multiply it by cosine of, and it's going to be 1/2 of the sum. Oh, so I think I fibbed to you a minute ago. I think I told you that this guy's wiggling twice as fast. This guy's actually wiggling at the average of the two frequencies. So that would say that it's actually wiggling just as fast as the first one was, or very close to it. So I fibbed a little bit. The trickiest factor of 2 in all this stuff is that you might look at this and say, oh, so with this right here represents, if you think of this as the amplitude, if you think of this as the amplitude of this wave, so this cosine wave that's what you get if you just have something that's wiggling at this rate and with the same constant amplitude, cosine of just the average of the two frequencies here. And just think of this as slowly modulating the amplitude of that sine wave. Well, you look at this and say, oh, I see, it's a half times the difference. Well, then that must be what's called the beat frequency. Well, the beats, I'm going to play it for you right now, and you'll hear what it sounds like. You've already heard it, but I'm just going to remind you what it sounds like. The beats we're talking about are these moments in time when the amplitude goes to 0. But notice that the amplitude goes to 0 twice during a full cycle of this longer sine wave. So what I've drawn right here is actually this one full cycle. No, it's half a full cycle. It starts off low, and it goes high, right? You have to go another whole distance, same distance, to go through 2 minima in the amplitude. So then you get 2 beats per, anyway. So the upshot is the thing that we call the beat frequency is just, oh, sorry, I'm completely wrong thing, is just this. The beat frequency is just equal to that difference, omega 1 minus omega 2, without the half in it. And the reason is because there's a half there, but then you get 2 beats per cycle of that outer sine wave. All right, so just to make sure everybody understands what we're talking about, I'm going to go ahead and play what this sounds like so you can hear it, and I'll have the oscilloscope and see if I can do this. I think it's already set up so it can go up to the cameras. Working. There it is. Yeah, all right. My voice has lots of things going on. It doesn't make a sine wave. In fact, it's the sum of many sine waves. But when I whistle, then you can see a perfect sine wave. Almost. Pretty perfect. It's much more sinusoidal than my voice, right? Now I've got a couple tuning forks, so I'll hit one of them. Right, that's a nice sine wave. There we go. And I'll hit another one. You hear it going, wah, 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 right? Yeah, it's really clear. So when you see it doing that wah, 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 routine, the amplitude going up and down, that's this. That's this thing right here. And I chose the two frequencies to be pretty close to each other, but not exactly the same. I made omega 1 and omega 2 pretty close together, right? And the reason I did that was to make this really long, to make the wave, well, it's not the wavelength, right, the period. To make the period longer, make 1 over the beat frequency really big, right? So you can hear it, take a while between beats. You're tuning an instrument, somebody plays an instrument, and then you play your instrument, and you hear this beat, wah, 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 and you keep changing whatever, depends on what instrument it is. You keep changing whatever lever you've got to change the frequency until you don't hear those beats anymore, and then you've got omega 1 really close to omega 2. So the beat frequency is so small that it's a long time before you get to a beat. So anyway, so I prefaced all this by talking about linear superposition. This is an example of linear superposition. To figure out what the resulting waveform looks like from those two tuning forks put together, what did I do? I just said, well, I know I get a sine wave from one, I get a sine wave from the other. They're both just simple harmonic oscillators, essentially, just oscillating sinusoidally. And if I add them together, I get this other shape. Now, as you notice, I know I may have made it seem more complicated than I should have, but you already get some pretty complicated stuff, some interesting stuff, just by adding 2 sine waves together. You add 50 sine waves together, it can get arbitrarily complicated. And in fact, it turns out, this is the magic of Fourier analysis, any possible thing you might want to represent, any possible shape you can imagine, you can represent by adding up enough sine waves. And there's a standard procedure, a straightforward prescription you can use to do that. It's a little beyond the scope of this class, but in the 7 series, that's part of what you do in advanced physics classes. You use it all the time. You use Fourier analysis all the time to take a really complicated shape or function, break it up into its Fourier components, i.e. break it up into sine waves, and then solve whatever equation you want to solve on each sine wave individually, and then add the answer together when you're done. It's a standard thing to do. But anyway, so for the purpose of this course, the main thing to learn is just that linear superposition is the way physics works. The sound wave you get when you've got 2 different sine waves is just the sum of sine waves, and that's what you get. And phenomena like beat frequencies and things like that can be easily understood in terms of just adding them together. So linear superposition, that's an example of, so here's constructive interference. When you add 2 things that are very similar, and you get a big result. And then destructive interference, adding a big positive number to a big negative number gets close to 0. So constructive and destructive interference in the context of an oscillator. These are a pair of oscillators. Now, how about waves? So when you've got waves, you can have destructive and constructive interference, not just with time, but in space as well. So the shape, so in other words, I could ask, we can ask questions about some shape of a wave in x and y in this rope and say, well, for example, when I hit the rope and I make a little bump in the rope and the bump travels down the rope, I could represent that as a sum of sine waves, right? And in fact, that's what physicists do when they want to calculate what can happen. So let's see, let me do a couple more things about interference. So I think this is a good warm-up for thinking about interference with waves. This is the instrument I played when I was in school. It's called a quink, and it only can play. It's not a very beautiful instrument, actually. I'll be honest with you. But back here, there's a little oscillator that makes a tone at some frequency, and the volume is controlled by moving the slide up and down different amounts. Can you hear it? All right, I told you it wasn't very beautiful, but I'm going to change the length of the path. So what you can see is, so you've seen lots of instruments, right, where there's, here, I'll turn it off for a second. So it's tough to handle. So with a trombone or something like that, or a trumpet or tuba, whatever it is, there's all this winding pipe, but no one builds an instrument like this, right? You never have 2 possible paths that take you from the mouthpiece, right, where there's an oscillator, your lips are making some oscillation, and then there's a wave, a sound wave that's traveling inside the pipe, right? Well, no matter how much winding you got in your instrument, you never pay money for an instrument that has a connection that goes like this and like this, right? There's only one connection that goes from the front to the back of the instrument, or whichever way you call front and back. But this is to illustrate interference in a sort of straightforward way. Yeah, right now I've got it set up so that the distance along here and the distance along here is the same. Okay, so that path length is the same as that path length, and you're getting a sound out. In other words, I'm causing constructive interference. I'll draw a picture of that in a second. So that's why it's good and loud. Constructive interference. Now, if I lengthen this, I can find a spot where it's destructive, and it's very quiet. I made the path length here longer than here. How much longer did I make it? So if it's full on loud right here, and I increase that length until it gets really quiet. If I keep going, it gets loud again, right? So if I go back to where it was quiet, then what's the difference in path length between here and here in terms of the wavelength? Do you know what I'm asking? Think about that for a second. I'll draw a picture of what I just did. So, okay, let's go back to this board over here. Oh, with a piece of chalk, preferably. Here we go. I got to put this in, I got to lock out my chalk. So if I've got 2 paths that the sound can take, I've got some sound maker right here, here's my speaker, right? And I've got a path along here, and I've got a path along here. And then here's the sound coming out at some frequency, some notes, so that's supposed to be. Well, if those lengths are the same as constructive interference, and let's think of exactly what I mean by that. Suppose that if I start here and I go along let's see, how can I draw a picture of this? I want to count how many path lengths, how many wavelengths it's gone through. And I drew myself too small of a picture. Maybe I'll make the pipe a little bit thicker. Let's do it this way. See, the pipe looks like this. So, and what I'm doing is I'm drawing sine waves. There's one sine wave. I'm drawing along the path. There's another sine wave. There's another sine. Okay, so I just did 1, 2.5. The 2.5 sine waves, let's say. So 2.5, in other words, this length, let's say that length is s, equals 2.5 lambda, right? And let's say that up here it's only 2. So it goes through 1, and it goes through 2. Well, in that case, when the waves come together again, one around the top and one around the bottom, they'll be out of phase by exactly half a wavelength, right? And that's going to be destructive interference, because that's like adding together a wave that looks like this to a wave, so that's one wave, to a wave that looks like this. So if you added those two waves together, you'd say, well, here I got 0 plus 0, that's 0. Here's positive amplitude A minus amplitude A. If you add those together, you get 0, right? So here's what you get bottom 0. Everywhere along the way, this guy cancels that guy out. That's destructive interference. So if I make the path length different by exactly half a wavelength, which is what I just did by raising it up a little bit, then I have destructive interference. And when they have equal lengths, or if the lengths are different by an integer number of wavelengths, then I can have constructive interference. You're going to see this over and over and over again in this class and in 8B, this notion of constructive and destructive interference. And the game is you figure out what the difference is in wavelengths between two different paths something can take, light or sound or whatever it is. Right? And this is the simplest example I can think of. We have a demo, right? Where there's only two possible paths. You can see them with your eye. That's the sound wave goes through there, and you can measure it with a ruler and say, yeah, this distance is greater than that distance by some amount. And so right there, we can eyeball it and see that the length's the same. We can measure the tape measurement's the same. And I pulled it back some. And so if you were asked, okay, how far do I have to pull so that you get exactly, so the sound goes away entirely? Well, you'd say I have to pull it by, actually, since when you pull it up, both sides are increased by the same amount when you lift it up. So I guess that distance must be a quarter of a wavelength, right? Because by pulling it up enough so I went from full volume to quiet, I added a quarter of a wavelength there, quarter of a wavelength there, so overall I got a half wavelength addition here, so then you're exactly out of phase. Half a wavelength is out of phase, right? Destructive interference. So anyway, that's the simplest example I've got of constructive and destructive interference, really. A more complex example that's a little more fun to think about is two speakers. So now what I'm going to do is I'm going to turn on these two speakers, and depending on where you are in the room, you'll either hear constructive or destructive interference based on whether the path length from one speaker to your ear and the other speaker to your ear is equal to an integer number or a half integer. Let's see. Yeah, whether it's equal to an integer number or an integer number plus a half of wavelengths. And I'll draw a picture of it in a minute, but let's just do the demo. So what I'm going to do is drop on the side like this. I'm going to rotate it, and you'll hear it get loud and quiet, and so I'll stop. And I'll say, okay, raise your hand if you are now in the loud zone, in a zone where you hear the sound really loudly. And we'll see if your hands can form a pattern in the room, see if this works. Okay, so I'll start it up. Okay, so they're both on. I'm going to start rotating. Stop it there. So raise your hand if it's loud where you are now. Oh, I should turn my microphone off. Done. Now I'm turned on. I'm so loud, I don't need a microphone for all of our friends on YouTube. Anyway, all right, so we're spared for a few moments. Okay, so here's the idea. If you have two sources, as we just saw, source 1, source 2, they're both emitting spherical waves of sound, right? I'm just going to draw a cross-section of that. So sound wave, right? These are wave fronts coming from each of these sources. See how good a job I can do drawing this. Okay, here's the other one. What does that look like? Well, it goes like this, like this. What you find is that this is a snapshot. This is one moment in time. And I'm asking the question, where do I get constructive and where do I get destructive interference? Right? So it's kind of hard to look at, but you see a clear pattern, right? Whenever you see the two lines cross, that's where the maximum value of the air pressure from one speaker is also the maximum value of sound pressure, from the other speaker, right? And so they constructively interfere. And what you should see are, if I did a good job of drawing this picture, you'd see stripes. You'd say, oh yeah, there's a stripe along here, and there's a stripe along here. It works for a bit, and then I get sort of veers along there, and so on. It's a pretty complicated picture, but the basic idea is that you get a clear pattern of radiating stripes of constructive interference. And similarly for destructive. So destructive is in between these. So here's a place right here, right, where from the left speaker you're at a maximum, but from the right speaker you're at a minimum. So you have destructive interference. You're very quiet right here for somebody. Whereas right over here it's going to be loud because they're both constructive, right? And so on. So you get this pattern, and that's what we should have seen with the hands. And I sort of saw it in some places, although the room is sparsely enough populated, it's a little bit, it's tough to know. There's too many islands of people in the room to know whether the stripes are just nobody sitting there versus the sound is quiet. But that's the sort of pattern we would expect. And here's another demo, a physical demo to sort of give you an idea what that looks like. This is just a physical, three-dimensional wooden model of the sound pressure level as a function of space in a snapshot. So here's a speaker over here, here's a speaker over here, right? Each of these speakers are producing sound with the same, oops, wow, it's falling apart, with the same, must follow me or anybody else, producing the sound with some particular frequency, and so the frequency is the same, right? The wavelength, in other words, is the same, but depending on where you are in the room, like if you're right in the middle, so you have equal distance from the two speakers, then sure enough, you get constructive interference because they're both sine waves are at their maximum at the same point. But let's move over a little bit. The guy sitting over here, right? Well, sitting right here, he's getting maximum here and minimum over here, and they're canceling each other out, getting destructive interference. So it's loud here, quiet here. And then it gets loud over here again, right? Because these two are lined up. They're not the same number, they're not the same distance, right? There are more wavelengths along here than along here. But that's not what matters. What matters is whether it's an integer number, whether the difference is an integer number of wavelengths. See that? As opposed to a half integer. So in this case, they're off by half a wavelength, they're off by one wavelength, they're off by 1.5. So when I say a half integer, what do I mean? I mean take an integer number of wavelengths and then add one more half integer. You might say, well, yeah, well, any integer is also a multiple of a half. So it's important to say, okay, the difference between the two is a half integer, or the difference between the two is an integer. How do I say it? The difference. Yeah, mod 1. Oh, it's awful. I can't say mod 1. Anyway, I hope the idea is clear, but I just want to distinguish between saying that it's a multiple of a half integer versus take the difference and then see if there's a remainder or not after the integer, right? If the remainder is a half, then you get destructive interference, like you do right here. But right here, it's exactly an integer number. They're different by exactly 3, I think. No, by 2, by exactly 2. Anyway, so that's the basic idea in pictures of what you should experience. And that's why I did go loud and quiet as I moved these things around. You're in different positions relative to the two speakers. So musical instruments are a major, it's a really obvious area for waves. We've been talking so far about traveling waves, but now we're going to talk about real quick standing waves. So again, going back to our rope, we can think of this as a string on a guitar or something like that. And if I'm some great guitar player and I strum that string, I can make a standing wave. So here's a wave that is not traveling to the right or the left. It's not moving anywhere, and yet we still think of it as a wave. But if we think about linear superposition, I can actually represent this standing wave that's just going up and down, right? No obvious motion one way or the other. I can think of it as the sum of a wave going that way plus a wave going that way. And so it really is a wave. It really does have energy. And we can figure out what the wavelength has to be based on the fact that the rope is tied down on both sides of the room. And if we've got some string that's got some velocity, we can calculate it in that formula. We know what the velocity of waves are going to be, the wave speed in this medium, in this rope. We can also figure out what the frequency must be. So the way you tune a guitar is you change the tension, right, in the string, and you leave the length fixed, right? The lengths of the strings are fixed, you tighten it and you loosen it, right? When it gets tighter, the frequency goes up, right? And then if you want to calculate what frequency is it that you're going to get, you take the velocity from this sort of a calculation, and you take the length, and from velocity and length, you can figure out what the frequency has to be. So let's see if I said that right. And let's figure out how to think about this stuff. Obviously, we're getting close to the end of the class. We'll have to revisit pipe organs and things next time, most probably. But the way it works with a string is that the two ends are nodes. A node is another name for a node means something that stays 0 all the time. So if you tie down the ends of the rope can't move up and down. So it's a node as far as the displacement of the rope is, over time. It's never going to move. So the rope's going up and down like that. This is a standing wave. Let's say that the length of the rope is L. Okay. I want to know what's the wavelength of the standing wave. Well, you can have lots of standing waves that satisfy this situation here, right? We can have this standing wave. You can't quite see on the board there, but it's just one big standing wave. But I can have this standing wave as well, right? Where there's it's not working. See if I can do it. What I'm trying to do is get so there's one node in the middle. That's kind of it right there. See that? So there's a node in the middle. Sort of worked. I can also, if I wiggle even faster, I can have 2 nodes. Is it working? And I can have 4 nodes and so on. Now it's getting better. That's pretty good. I can go faster. And, I think I can. There, sort of. There it is. Sort of see it. Anyway, so the idea is by changing, there are different frequencies associated with these higher harmonics. This one right here, the one that just goes up and down for the whole guy, that's the fundamental sort of oscillation. That's a fundamental frequency. And we're getting low on time, so I'm going to go through all this stuff next time. But the basic idea is you have some length of the rope. You break it up into integer numbers. Or actually, it doesn't always integers. We'll go through it next time. But there's ways of thinking about how to relate the wavelength and therefore the frequency of these different standing waves. And it's going to work out to be the same for, it's going to turn out to be a relevant idea, whether we're talking about sound waves in a pipe organ or longitudinal waves in a rope, standing waves in a rope. All right. See you next time.